Okay, so we're just going to kind of talk about the general gist of this stuff today and maybe do one example if we have time of partial fractions. Basically, the goal of this stuff is to take some kind of a function that's a rational function, so it's going to come in the form f of x over g of x, and then turn that into two fractions, two or more. I guess technically you can do more, but we're going to stick with the easier ones, just a couple to start with. And so we're going to take factors of g of x, and those become the denominators. And then we need to figure out what has to go on top for a and b so that it equals the fraction that we started with. What this is basically just the process of taking some kind of a addition or subtraction of fractions and working it backwards. So rather than like doing the whole common denominator thing and then pulling them all together and making one fraction, we're used to going that direction with it. In fact, you've done that since about Algebra 2. We're going to try and take it the other way now. So if I have it as one whole fraction, how can I bring it back to that? Now, why in the world would you ever want to do that? Well, in calculus, there are some integral calculations we need to do that if you were to leave it the way that it is at the beginning, you can't calculate it by hand. But if you can break it apart into separate fractions, then you can, as long as those fractions are less complex than the one you started with. And if you do this process correctly, it will be. So that's kind of the goal. It's a specific thing in calculus that's kind of driving it, but better to do it now, and then when we get to that stuff later, we can kind of keep rolling through it in AP Calculus. So in any event, let's take a look at how this goes. We'll do one kind of quick example here, see if we can knock it out. So yeah, this will be a good one. But we look at y equals 5x minus 1 over x squared minus 2x minus 15. Okay, so when I put this thing together, the common denominator must have been x squared minus 2x minus 15. Okay, so if that's the case, then what would be the two denominators of the fraction we started with? Or the fractions we started with? X minus 5 and x plus 3. Okay. Okay. Because those would have been, the factors of that. X squared minus 2x minus 15. So then the only question is, okay, so what goes up here and what goes up here? So A and B, we're calling them capital A, capital B. We're going to try and figure out what do those two need to be to make this thing happen. Okay? And so the way that we start that process then is to think about this whole thing here is one big equation. And what could we do to that to simplify it a little bit? I.e., get rid of the fractions. Multiply everything by what? Yeah. If we multiply through by x squared minus 2x minus 15, wouldn't that cancel all the denominators off? It would leave you with some things that you would have to multiply in some of the numerators, but it would cancel out all the denominators at the same time. So we're thinking about taking this whole thing, and if it's easier, why don't I write it like this? So it's x minus 5, x plus 3. Maybe then it'll be a little easier to check out what's going on. Okay, so if I take this entire thing and I multiply by x minus 5 and x plus 3, okay, think about distributing that to each fraction. What's going to happen? Okay. Mm-hmm.
Like leave x plus 3 on the bottom?
Not on the bottom, because you're multiplying this, right?
Oh, okay, yeah.
So if I take this and multiply it over here to this fraction right there, the x minus 5s will cancel, but the x plus 3 will still be on the top, right? So we can do that and not have any fractions left over. So the first one, the entire denominator is gone, and nothing happens to the numerator because it's just a pretty clean cancel there. A is going to get multiplied by x plus 3, and B is going to get multiplied by x minus 5. So we've drastically simplified this thing up now, right? Okay, so now still have the challenge of trying to figure out what's equal, or what's A and what's B, and how we use this to figure that out. Okay, well, let me distribute some stuff here for a second. It's going to seem like I'm making this thing more complex, but it's actually going to help us out here. I distributed the A and I distributed the B. That's what I did there. And then I'm going to do a little rearranging. Okay. And basically what I've done here is I've broken it into some different groups. Things involving x and things not involving x. Okay? And I have some equations from that. So, this should be equal to ax plus bx. Because the x's on either side of this equation are going to have to stay balanced, right? So if I have 5 of them over here, and I have a plus b of them over there, then 5 should equal a plus b, right? Okay, so let's jot that down. 5 equals a plus b. I don't have to worry about the x's anymore, right? Because I have this many x's on the one side, this many x's on the other side, so 5 should just be a plus b, whatever that is. And then we also have don't involve x, so negative 1, and then this 3a minus 5b. And those should be balanced as well. Negative 1 should equal all the constants on the other side then. So negative 1 equals 3a minus 5b. What have I just created? A system of equations, which is why we did the section previous before this. So now this is nice. It's just a 2x2 system, which is pretty straightforward. So we can encode it in a matrix and try and do that, or we can just do some substitution elimination, which is probably going to be where you want to go with this one. So what do you think is going to be probably the easiest way to roll on this? Do a substitution? Okay. How would you like to do that? That works. Take that and substitute it into the other one then. So we get negative 1 equals 3 times 5 minus b minus 5b. And then we should be able to take that and solve it for b, and then use that answer to figure out what a is. So negative 1 equals 15 minus 3b minus 5b. So if I add the 15 to the other side, that's going to be, or no, subtract it. So negative 16 equals negative 8b. So what's the value of b? B is 2. Good. Look at one of those equations up there. What's a? 3. Yeah, okay, good. A and b, that was really our goal here, right? So we can go back and rewrite our partial fractions for this original rational function that we had. So what we got, minus 1 over minus 2x minus 15 is equal to 3 over minus 5 plus 2 over 3. Okay, we're able to break this down into those two fractions.
Would it matter if you put the x plus 3 first and x minus 5 last? So it was a all over x plus 3?
Mm-hmm.
Would that make a
Correct. Yeah.
You still get the same answer.
Exactly. Yeah. So well, if you had it switched, yep, you just have A and B being the opposites of each other, and then this answer ultimately would be the same thing then.
Okay.
Yep.
Are we going to do anything beyond breaking it up into these two fractions? Are we going to like solve for x from here?
Nope. Nope. This is the goal, doing this type of thing. Now, as far as where are we going from here? Sometimes there are 3 partial fractions. Sometimes there's more. Sometimes,
Three of the denominator.
correct. And sometimes, instead of just a number over a factor and a number over a factor, you might have, like, on the top something involving x. Like 2x over x plus 5 or something like that. So we're going to take a look at where this can go that way on Monday then. Okay? Expanding it out that way and how when that happens and that sort of thing. So, all right, I'm going to stop my recording now. All right, so I got another one here for you guys to take a look at. Remember our goal with partial fractions is we're trying to take this rational function and break it up into some smaller fractions that if you were to then go ahead and do your common denominator and add them together, it would equal this. So it's doing like a fraction addition or subtraction. We're trying to undo it. Now this one's got something different going on from the last one. Well, I guess a couple of somethings. That's the first something. It's x cubed on the bottom instead of x squared. Now, that doesn't really affect the process necessarily so much. We're still trying to figure out what are all the factors of the denominator and then use that to make fractions. Okay. Now, the difference with this one, though, that we're going to see is once you factor that denominator, you're going to have a factor that is repeated. Okay? So, like, for example, this thing breaks down into x times x squared minus 4x plus 4. But if you factor x squared minus 4x plus 4, what do you get? Exactly. You get x minus 2 happening a couple of times. So you could factor it, I guess, like that then, right? Now, how that affects the partial fractions, just based on how together works, if you have a repeated factor, it's not as simple as just, well, I'm just going to put x minus 2 under 2 of them and then call it good. Okay? So we'd still have the first one for x, but then we'd have b over x minus 2, but c would be over x minus 2 squared. Because if you're adding fractions together to make this thing, one of them might have had x minus 2 squared underneath of it instead of just an x minus 2. It only happens when you have repeated roots, though.
Isn't that too many factors?
We're going to end up with a little bit more on the one side than the other, but the process can still work that way, though. I'll show you. It's not a problem. Okay, but that's the only thing you need to remember here, though, when setting these up, is if you have a repeated factor, okay, you have to use it more than once. And each time, like this one is just x minus 2, then this is x minus 2 squared. So each possibility that could have happened could have been just an x minus 2 in the mix or an x minus 2 squared, since this has 2 of them in there. So you use each more than once. Okay, and I won't make it any more complicated than this. Okay, a simple linear factor repeated twice at most. I'm not going to do like x minus 2 cubed or something crazy like that, in which case you would have to go x minus 2 squared, x minus 2 cubed. You'd have 3 of them then if you did it that way. I'm not going to go that way. Like if you guys ever take linear algebra someday and you're doing this sort of thing, you'll do it then. But for now, it's not going to be any crazier than this. And honestly, when we get to AP Calc and we're using this, like I talked about on Friday, how we need to do this to do some integral stuff in calculus, it never gets any worse than this either. Okay? So, in any event, let's take a look at what we got here, though, and see if we can apply what we learned about on Friday to something like this. Okay? So what did we do to get it started after we had it broken up like this? If you need to page back in your notes and take a look, go for it. What was the next step? Yes, sir. Essentially, yes. But what did we do to take care of that? So we were trying everything over x, like in this case it would be x cubed minus 4x squared plus 4x. And then we were able to wipe out all the denominators because they're all the same. But what could I do like all in one step though? Like the next thing was to wipe them out. So what do you do really to get rid of all of them? I think we did do that Friday, didn't we not? Just multiply by it, right? Multiply by that denominator and that cancels them all out. So, like this first fraction, we'd be just left with negative x squared plus 2x plus 4. So then what does a get multiplied by? Well, it's already got, remember, we're essentially multiplying everything by this, correct? Which is the same as this. So if I multiply this first fraction by this, it cancels the entire denominator. If I multiply this, x times x minus 2 squared, by this fraction, the x's cancel, right? What's left behind then? Right. Does that make sense? A times x minus 2 squared for that term. And then the next one, again, I'm multiplying this by this fraction. What cancels? So you'd be left with x times x minus 2. And then the last one, I'm multiplying this by this. So what's left over? Just the x. So that would be cx. So that was that step of getting rid of all the fractions. Okay, and then from there, what we did was we tried to match up all the x squared terms and the x terms and the constant terms, which we can still do. Okay, I do a little multiplying things out and distributing here on the right-hand side to be able to set that all up. So we're looking at negative x squared plus 2x plus 4 equals, let's see, if I multiply this out and then distribute an a, should be ax squared minus 4ax plus 4a. That's all just from here. And then the next one, if I distribute the bx squared minus 2bx, and then I got my cx. And then we kind of grouped them based on x squared, x, and constants. So negative x squared plus 2x plus 4 equals ax squared plus bx squared. And then all the terms that have x in them, minus 4ax minus 2bx plus cx. And then the constant term, there's only one. This is 4a plus 4a. And so everything should match, right? So this, the coefficient on x squared there, should be the same over here. So negative 1 should equal a plus b, right? And the coefficient on x should be all the coefficients on x over here. So 2 should equal negative 4a minus 2b plus c. Bless you. And then we've got 4 that needs to match with the 4a because that's the constant. So 4 equals 4a. Now, yeah, this system, you don't have to turn into a matrix and all of that business. You could, and you would be able to solve it, and it would be just fine. But if you look at the way that this thing is set up, it's set up in such a way that you could go through and find A, then find B, then find C, right? So just do that, okay? If it presents itself in a way where you can just logically get your way through it, do it. If you want a method that always works, but might be more work, turn it into a matrix and do your thing there. But you don't need to. So just looking at this, what is the value of A? 1, right? 1, what's the value of B? -2, right? And if A is 1 and B is -2, well, maybe we should plug into that one at least. So 2 equals -4 times 1 minus 2 times -2 plus C. So that's -4 plus 4. Oh, that kind of works out nice anyway, doesn't it? So what is C? 2, yeah. All right, so we got the A, the B, and the C, which is what we need. And now we can go back to the original decomposition of all those fractions and write out our answer then. Okay, so we're going to have -x squared plus 2x plus 4 over x cubed minus 4x squared plus 4x equals, A was 1, so 1 over x. B was -2, so minus 2 over x minus 2. And then C was a +2, so plus 2 over x minus 2 squared. There's the partial fraction decomposition for that one then. Okay. Now, there's another way to do this. If you don't like the little systems of equations and you don't want to have to do a matrix if it's necessary and all of that business, there's a step in here that I'll come back to where you can kind of play around with it a little bit and maybe, sometimes you can't, but maybe get some answers a little quicker. Okay? So let's go back before we ever did any of this multiplying out stuff, back to this step right here. Okay? Where I have the -x squared plus 2x plus 4 equals A times x minus 2 squared plus bx, blah, blah, blah. You are allowed at any stage here, if you want, to plug in whatever number you want for x and see what you get. See what happens. Okay? Because in an equation, right, the left side should always equal the right side, no matter what you plug in for x. So sometimes there's a convenient number for x that you can plug in to make this thing work out a little nicer for you. Okay? So if you look at this equation, I want a number for x that I could plug in where a lot of things would kind of just go away. Anybody think of a good number we could use there? 2. Well, what would happen if we plugged in a 2? So, get this thing down here, and let's just explore this a little bit. Okay, so if I were to put in a 2 inside of this thing, I would have -2 squared plus 2 times 2, so that would just be, and then plus 4, so it'd just be 4, right? So I'd have 4 equals, what would happen to this term right here? It's completely gone, right? 0. What would happen to this term right here? Completely gone. Including this one, including the A, and this one, including the B, right? Just totally gone, all 0. What are we left with then? Yeah, C times, so 2C. So what's the value of C? Right there. I don't have to do any multiplying out. Okay. Now, can anybody think of another value of x that might be convenient to help us get rid of a bunch of stuff? Go back to the first one, this line at the top here again? 0 would be a good one, sure. So what happens to this left-hand side if I plug in a 0? It'd be 4 again, okay. If x is 0 right here, what do I get? It would be 4a, right? Okay, 4a. And then what about this term? 0. And this term? 0, right? So what's a? 1. Okay, so I've already got C and I've already got A. Now I just need to figure out a way to get B. Okay, well, plug in the C equals 2 and the A equals 1, and then whatever number you want for X, and you should be able to then solve for B, right? So maybe we plug in it can't be 0 or 2, because those will get rid of stuff. Maybe a 1? Sure. So if X equals 1, we've got negative 1 squared plus 2 times 1 plus 4. So that would be 5, right? Okay. We know is 1. 1 minus 2 squared, that would be negative 1 squared, so 1. Plus b we don't know, times 1. 1 minus 2 is negative 1. And then plus c we know is 2, and x we said was 1. So we just do a little simple math here. We got it. So 5 equals 2 minus, sorry. I'm adding instead of multiplying. So 1 minus b plus 2. So 5 equals 3 minus b. So b needs to equal negative 2. So a, b, and c, right? It's all about picking those convenient values of x. So, and this works most of the time. So if you have a system, when you're done, like with the A and the B and the C, like this little system we came up with, that was pretty easy to solve. It's not always going to be that way. So if you got a system that you're like, yikes, now I'm going to have to start doing row operations or make an inverse matrix or something like that, I don't want to mess with that, go back to where you were here and see, is there a convenient value of x that, if anything, gets you at least one of the A, B, or C's, and then you can start putting those into here and do it that way if you want. Or if there are other convenient values of x, like we found when we could do a 2 and a 0 and get stuff easily, then you can just rock and roll from there and you're done. So it's kind of up to you what you want to do, but it does help get through stuff. So take a look at here, which is if you don't have linear factors, what if you have quadratic factors in the mix? What do you do then? And if we're good there, then we'll be done. And we'll use this same kind of trick to help us get through it too. All right, so we're going to do x squared plus 4x plus 1 over x cubed minus x squared plus x minus 1. We want to do the partial fraction decomposition for that one. So we need to figure out what are the factors of the denominator again, right? So how do we factor x cubed minus x squared plus x minus 1? We can. It's the method that everybody always forgets about. If there's 4 terms, you can try something. It doesn't always work, but you can try something. Yeah?
Didn't you do that like that one thing?
Yeah.
Like finding the one term.
You gotta be more specific. What one thing?
You know, what is it first you forget? When you find like the
Right. What's that called? We look at just the first 2, find the GCF, and then the last 2, find the GCF. It starts with a G. Grouping. Yeah. Oh. See, I told you, everybody always forgets about it. Yeah, so I'm just going to rewrite the denominator here so we can work with it kind of cleanly. Yeah, so what's the GCF of the first? X squared. So we take x squared, what's left? X 1. GCF of x and minus 1. 1, so plus 1 times x minus 1. So the factors are x squared plus 1 and x minus 1. Now I said this doesn't always work. If these two parentheses are not the same, it's not going to factor then. That has to happen. But if it does, then yeah, we got something right here. So our two for this one, nothing repeated here, right? It's x minus 1 and x squared plus 1. And x squared plus 1 does not factor any further. It is not x squared minus 1. It is x squared plus 1. You're stuck. Can't go any further. So we've only got two fractions, 1 and x minus 1. Now, here's the thing. If you have a quadratic denominator, then your numerator doesn't have to be, but it could be linear. Up to this point, it's always just been a constant on top of each fraction, right? A, B, C, or whatever. So in this case, because we've got something quadratic underneath there, whatever's on top could be at 1 degree lower or even lower than that. So it could be just a constant on top of this thing, but it could be something linear, something times x plus something. So to make sure that we cover our bases with that, we got to make this ax plus b. Okay, could be linear. So ax plus b we need to put there. And then the other one, x minus 1, that's linear, so it's okay just to put a constant on top of that one then. So just a c on that one then. Okay, so be careful. These two that we've been looking at here, these are the concepts that always throw people. The first one is that repeated root thing, and that's in the right way. And in this case, it's a quadratic, or an irreducible quadratic factor, technically. That have something then linear just in case on top of it. Okay, it might be that a equals 0, in which case it would just be b over x squared plus 1. It is just a constant. That does happen. For sure, so we got to make sure we got something there just in case. Okay, so let's go going then. We got to multiply by the denominator left over then. Okay, so x squared plus 4x plus 1 should equal ax plus b times what? C multiply by what? I think I heard it, but I'm not sure. Yeah, good. Okay, so there's our setup. So, you guys want to try the convenient value of x method here and see if we can get something? Everybody see a convenient value of x? Yeah, 1 would work, right? Both a and b, and leave us with a way to find c if we did that. So let's try that. We'll just start that way this time and see if it works. So x is 1, so that gives us, let's see, this side would be 1 plus 4 plus 1, so 6 equals, this whole thing would be 0. Plus c times 1 squared plus 1, so 2. So yeah, so what's the value of c then? 3. We got c. We still got to go back and find a and b. Are there any other convenient values of x that would eliminate anything else? So if we plugged in a 0, would anything cancel out in this case? It would cancel out a. That's true. So maybe we could still do that. So I get rid of the a. We'd have b times that. Sure. Yeah. All right. Cool. That works. Nice. I didn't notice that, but yeah, right in the middle of that factor, it works. Typically, you try whatever's going to make this 0 or this 0, but in this case, that does take care of the a, though, so we're good. Yeah. Don't want to do that. If we put in a 0, we're going to have 1 equals, it would be, yep, negative 1 times, so I'll do it this way just because it's in the same order, but b times negative 1 plus c, we already know is 3, so 3, and then a 0 into this gives us 1. So, yeah, we got something that'll work there then. So 1 equals negative b plus 3. So we subtract the 3 to the other side. That's negative 2 equals negative b, so b is 2. So we got c, we got b. Now we got to find a. So what could we do to find a then, once we know the other two? Yeah. Value you want for x, and just roll with the b and the c we already have. Should be able to find a. So what number would you like? Negative 1? Okay. Oops, negative 1. Negative 1 squared is 1, plus negative 4 is negative 3, plus 1 is negative 2. So we got negative 2 on the left. And let's see what we got over here. So that would be a times negative 2 plus b, which is 2. And then that would be negative 1 minus 1, so negative 2. Sorry. My fault. And then that's a negative 2, right? Negative 1 minus 1. And then plus c is 3. And then negative 1 squared plus 1 should be 2. Bless you. Alrighty, so we got, should be everything we need now. So negative 2 equals, if I distribute the negative 2, this would be 2a minus 4 plus 6, right? Because negative 2 times negative 1 is positive 2, so positive 2a. Negative 2 times 2 is negative 4, and then we got the 6 back here. So negative 2 equals 2a plus 2, subtract the 2, so negative 4 equals 2a. So a should be negative 2. So turn to the a. We do end up having a linear factor up there. So our and yes, I'm going to make you write this all out, because that's what the answer is supposed to be. So it's this original fraction equals negative 2x plus 2 over x squared plus 1. And then c was 3, so plus 3 over x minus 1. Would be that one all the way broken down then. So, good. Yeah, got it. All right. So, that's I'm going to make it. So if you have a repeated just once, or if you have a irreducible quadratic factor, something like that, just making sure you have the linear part on top of it, and then going from there. But get everything, once you get eliminated and you have it all set up, the same. So if you want to do your convenient value of x method, that'll usually get you at least part of the way. And then if you got to go through and start multiplying things together and matching coefficients to get it the rest of the way, then you can do that too. So I'm going to let you guys start working on this stuff.